All right, well, good afternoon, everybody. I think we can probably get started. So I'm Aaron Masino. I'm at the formerly Center for Biomedical Informatics, now the newly minted Department of Biomedical and Health Informatics. At least that's the name, as far as I know, this week. So formalities first, nothing to disclose. So I'm going to talk about our efforts to classify radiology text reports, in particular radiology reports related to CT scans of the temporal bones. And in doing that, I'm going to try to frame sort of how you go about doing applied machine learning for these kinds of problems, and also some NLP work, natural language processing tools that we've used. And again, just sort of keep this classification problem as sort of our motivation for doing this. So the research of interest that we are doing is we're trying to apply machine learning and natural language processing to, like I said, classify temporal bone CT impressions as normal or abnormal relative to the ear. We'd like to additionally be able to classify if the report is abnormal, which structures are noticed as abnormal, but we haven't gotten to that point yet. So why do we want to do this? So our group, along with some others, maintain AudGenDB. So this is the audiology and genetics database. It's a public research database for audiology, as its name would imply. And it currently has something on the order of 15,000 unlabeled radiology text impressions with associated images. And so the disadvantage to that being unlabeled is that a researcher who wants to come in and say, look at reports which only pertain to patients with some sort of abnormality are going to have to manually go through some percentage of these to find them, because there's no way to query the system for that. And so we'd like to be able to provide that capability. There's probably also some clinical utility, but this is our sort of primary motivation. And so we have a classification problem on our hands. This is a pretty sort of textbook kind of classification problem, but to just provide some sort of framework for that. So I'm not sure that everybody is sort of familiar with how you go about applying machine learning in this kind of context. It's kind of, you say machine learning and people go, oh, throw their hands up, and that's kind of scary. But the reality is, for these kinds of things, there's a lot of tools that make this very easy. So we typically start off with some kind of object that we want to classify. Person, place, or thing. Here we can imagine that we have some kind of, a patient population that we want to be able to make predictions about. And so we have to represent that patient in some format, so some set of numerical values that we think quantify the patient in a way that relates to the class labels that we're trying to apply to this population. So that could be any number of numerical values. Here I've just picked some things, this is made up of course, that may apply. They need not be purely sort of quantitative values. They can be categorical, so gender, race, things like that, but you still have to convert those to some sort of numerical value. So, gender might be indexed 0, 1, 2, 3 as representative of your different categories. So you have this information and you plug it into an algorithm. For now, let's not worry about where that came from. Let's just say we have this algorithm, you give it some data, and it does something magical and spits out a prediction on whether or not, in this case, say, the patient is sick or not sick. It doesn't have to be only two choices. You can have a multi-class problem where there's n possible labels, and it'll attempt to pick the one or more labels that apply. And so this is, a pretty straightforward concept. The question becomes, well, where does the algorithm come from? And there's multiple ways that you might get an algorithm. You can have a heuristic model where some domain expert will sort of intuitively, from their experience, be able to say, well, such and such features are important. I believe they're related in some way functionally to predicting the class, and they can sort of come up with this heuristic model. Another approach is from first principles. So here you're thinking you've got some fundamental laws of nature that you understand, or of the process in general, and from those you can derive more models to model your particular phenomenon. Now, this is something in medicine that we don't have a lot of, because it's very difficult to scale up from sort of discrete values about an organism and model that all the way up to a system level behavior. So another alternative is to get the model from data, and that's essentially what machine learning is. We're extracting model out of the data that we have. And so the particular class of machine learning problems that we're talking about here are something called supervised machine learning problems. And in those, I have a set of sample data for which I know the answer already, effectively. So this is obviously very contrite, made-up data, but you can imagine here that we've gone through and we have, that's not what I wanted. We have data that relates, we know the heart rate and we know the temperature of a patient, and at the same time, we happen to know whether they were labeled as sick or not sick. So sort of very simplistic data. And from that, we want to try to learn a model from that data for predicting on future patients. And so this linear model looks pretty good. I mean, it's doing a pretty good job of separating these things. I mean, we have some outliers that seem to be on the wrong side, but in general, we feel pretty confident in saying that, you know, if the combination of heart rate and temperature lie over here, then the patient's sick. Otherwise, if they lie over here, they're not sick. But there's some inherent assumptions here. Two in particular are that we've assumed that the features that we've captured, heart rate and temperature in this made-up example, adequately provide enough information that we can classify the patient with respect to the thing we're trying to classify on. The other sort of fundamental assumption is that the sample data that we have is representative of our general population. So in other words, if I build a model out of this sample data, does that generalize to the rest of the population that I'm going to try to predict on in the future? And so generally, those two things are actually not true. So you can imagine, for example, that maybe here, right, I'm predicting that this person is not sick with this linear model, but in reality, according to the label, they are. And so probably there's probably additional features that would account for that. But then we have other things like this, where this one is just sort of a clear outlier. Maybe some of the data was mislabeled. So the point is, we don't want to put too much faith in our sample data, and we need to control for that as we learn. So I'm going to get into just a touch on sort of how we do that. I'm a mathematician by training. For anybody who hasn't heard me talk before, I always try to put one equation in my talks just to make myself feel better. And then I'll try to explain it. So this one is just representative of the general form of output that we get from a machine learning problem. And all this really saying is that what we're going to learn is some function f, which takes some input that describes the object, a patient in this case, and gives an output on the prediction, whether it's a regression problem and we're trying to predict a particular number, or a classification problem, we're trying to predict a label. Regardless, we're going to get some output y. Now, the theta values are what we're going to learn, and so they just tell you how to weight the particular features that are coming in for this patient. And so they are fixed once you've learned a particular model. So they're fixed relative to the particular machine learning approach that you use and the particular data set that you have, as well as based on these learning parameters. So the learning parameter doesn't actually appear in the final model. This is just something you use to constrain how your learning process uses the data. And in particular, it's to control over and under fitting, which I'll get into in the next couple of slides. But at the end, that falls out of the actual model. So the linear model looked pretty good, but if we had too much faith in our data, if we believed very strongly that it was very representative of the general population, we might be tempted, based on this data, to create a model like this. Right? We're getting more of the particular samples that we have for the training on the sort of right side, the correct side of these boundaries. But in reality, this is sort of obvious that this is a classic overfitting problem, and we want to try to control this, and that's going to happen with a couple of different ways. We could either reduce the number of features that we use to describe our model, or we could try to change our regularization parameters, these lambda values, on how we use the data as we're learning. The other possibility is that we have too much bias in our case. Here we may be we're getting a situation where we sort of undertrusted the data, if you will. Clearly, this portion of data over here is not really being accounted for properly. And so either we don't have enough features, or our regularization parameters are sort of too heavy-handed, and we're not sort of accounting for the features as much as we should be in the weights. So these are some things we want to keep in mind as we work through the actual problem, to sort of evaluate how our model's doing and what we can do to fix things as we find that they work or don't work. So that's the sort of framework, the context we're working in. And so the real problem, right, we're trying to classify radiology text reports. So what do we need to do? Well, from the sort of background, we know we need labeled examples. And so, okay, we need to get those, that's fine, we can go label them. From those labeled examples, so now we have documents that look like an object, kind of our person in that sort of cartoon drawing. From those, we need to extract some kind of features that we can feed into the algorithm. Once we have that, we can train the models and evaluate and see how we do. So, okay, we have a training corpus of 252 radiology reports taken from AugenDB and manually labeled. We're working on getting more, but that's where we are right now. And they are labeled as abnormal if any of these particular structures related to the ear were noted as abnormal in the document. Otherwise, they were labeled as normal. So we sort of satisfied the first step. The problem we now have is how do we take text and convert it into some numbers, right? It was sort of very easy to talk about, well, we have a patient and we can say height, weight, maybe some other physiological parameters, and that's sort of intuitively kind of obvious to us. But how we convert text into a meaningful feature vector isn't always as obvious. One of the standard ways to do this is to form what's called a bag of words model. This can be surprisingly unclear what that actually means, so I'm trying to illustrate that here. So what you have is all of your documents, and you go through all these documents, and you want to find the sort of unique word set or dictionary that occurs across the documents. Now, you want to be careful with that, thinking back to the problem of variance, too much variance, or overfitting of our models. We want to sort of limit how many of these words we're going to use, because they're going to represent our features. So we start by limiting so-called stop words. These are things like the, of, common words that probably aren't going to provide any capability to discern one class from another with respect to these documents. And we also want to remove, we want to get just to the stems. So we really just want to represent base words. We don't need, so abnormal and abnormality are essentially going to be the same word to us. Different cases of tense for a given word will be the same word for us as well. And so this is where our first NLP tool, I say our, I mean the one we're using, not one we developed, called Natural Language Toolkit. It's a Python library, it's freely available, open source, and it does all of this for us. So this is sort of very easy to use. Basically feed in a set of documents, and it will return these word stems as well as removing the stop words. And so we end up with 1,200 words when we do this for our 252 documents. That's a lot of features. It's a lot of features for 252 sample data points. There's not very good rules of thumb for saying how many features is too many, but experience tells me that's too many features. So what we did here is look for a way to reduce the dimensionality of this feature set. In particular, we applied a chi-squared test. So essentially, we're looking at how correlated a given word is by itself with one class or another in the document set, and setting a threshold of a p-value threshold of 1% takes us down to 57 words. That seems like a more reasonable feature set. And so you sort of see the sort of flow here. To apply the chi-squared test, just using another open source library called scikit-learn. This is another Python library that has, in addition to some basic statistics, has a significant amount of machine learning algorithms pre-baked, so that makes our life a lot easier. We don't have to code all of this stuff ourselves. We can just go ahead and apply it. So we have 57 features. We still haven't turned each document into a vector of numbers, which is what we ultimately need to do. And so this bag of words approach is to take the word stems that we got from our word corpus and convert each document to a set of zeros and ones so for example, document 1, a 0 in this position means that this word did not occur anywhere in the document. A 1 in this position means the word did occur in the document, and we have a set of these sorts of bitwise values for every document. And so, for example, this document doesn't have any words, at least from this set, in that document. Obviously, I've only shown 4 for sake of room, but there's 57 of these. So now we have a bit of, okay, how do we train this thing? How do we validate our model? And so if you were to go out and read most of the literature that's available on the internet, particularly blog posts and things like that. If you're trying to learn how to do these things, what you would see is, okay, go ahead and divide your data up into 3 sets, one to train with, one to cross-validate with, and one to test with. The problem is that is very biased toward using for big data. So this has sort of proliferated the web and the data science community. And the reality is most of us don't have big data, and so it's not a very good approach because we just don't have enough data to do that. Certainly, I don't in this case. And so a more standard approach is something called k-fold cross-validation. K is typically 10. I've used 5 because I don't have enough data to do 10. But essentially what you're doing is taking your corpus, your set of training documents, and dividing it up randomly amongst 5 buckets in our case. And you will take 4 of those 5 buckets and use that to train your model. And you leave 1 as a holdout. And so after you've trained the model to learn these theta parameters, you'll test against the one that you held out. And when you do that, you'll get some evaluation metrics. So this could be accuracy, F1 score, whatever your preferred metric is, you'll get a value. And so now you repeat this process. You hold out the second set, you train against the other 4, and evaluate again. And so you get another value for your metric. Hopefully there's not too much variance in the metrics that you're getting, but you will get most likely get a different value. And so you repeat, so on and so forth, until finally you've gone through all 5 possibilities here, and you have 5 different metrics. And to report, you just take the average of those, essentially. Now, we actually repeat that whole process a number of times, 10 in our case. So your final reported performance is really an average of all of these. So that's an average of 50. And so that's how I'm going to be reporting the performance metrics as I move forward. So one point of clarification, I've seen this a lot when k-fold cross-validation is discussed, is, well, what's my final model? I mean, I trained 50 different models here and got 50 different sets of weighting parameters. What's the right one? Well, that's really, that multiple training is just to evaluate performance. At the end, you don't want to waste any of your data, and you actually train against the entire data set. And that was, so if you were implementing into a system, that would be your final model. So how did we do? With this bag of words, we've got a big table of numbers here. I do not expect you to read them all. I'm going to sort of go through the more important ones and why I have so many numbers. So we trained 8 different models. These are 8 different machine learning approaches. Again, not terribly important. As it turns out, most of them do about the same. Many of them behave very similar depending on the particular problem. The point is that if you're doing applied machine learning, these things are already implemented in whatever library you're using. I can use scikit-learn. So you don't really need to implement them typically. I mean, one exception, I had to implement the neural network just because it wasn't in there. But for the most part, you're going to find what you need already implemented somewhere. But what I want to point out is sort of the hazard of only looking at one set of values for performance. I see quite often accuracy is the only number that's reported. And so here we have pretty good accuracy numbers. We're ranging from roughly 82 to low 90s in accuracy. But I point out that of our training set, 76% of them are abnormal. So I could achieve 76% accuracy with a model that says everything's abnormal. Wouldn't be very good for the positive cases, but the negative cases, but it would be 76% accurate, at least based on this population set. And so I'm always a little skeptical when all I see is accuracy numbers. And in particular, for our case, I'm sort of foreshadowing about the negative cases. If you look at our negative predictive values, they're not very good, right? They're as low as 59% and only as high as 86% in the best model. And the reason for this is we're not doing very well on that sort of subset of negative cases in our sample set. So we're doing pretty well on the abnormal, but not the normal ones. Likewise, specificity is pretty low. I mean, as low as 48% and sort of an outlier high as 92%. And so kind of don't have a lot of faith that this is a good model. And if we dig in this a little bit further, another way you go about evaluating how well your models are doing is to use what are called learning curves. And so the idea behind a learning curve, and I will point out that I've stolen these images from Andrew Nee, who's at Stanford, but the idea behind learning curves is you train your model with 1 or 2, well, 2, we'll say minimum, pieces of training data, so 2 samples. And then you evaluate how well the model can predict those training samples and how well it can predict your test set. And what you're looking for is whether or not you have strong bias or strong variance, or maybe you shouldn't have both, but you can have a mix of both, certainly. So your training set will kind of look like this if you have strong bias, and it'll look kind of like this if you have strong variance. And that gives you some hints about sort of what you can do to improve your model. Do I need to add more features? Do I need to back off or increase my regularization parameters? Do I need to reduce the number of features? And so this is one learning curve out of 400 that we could have. Again, we trained 8 models. We did 50 training sessions per model for the cross-validation. Obviously, I don't want to show 400 learning curves, but this one's kind of indicative. We don't have, it's not obvious that we have a lot of strong bias, but it is there as we're sort of increasing. We're not really bringing down the training error or the test data, which is a little bit of indicative of bias. But we're also got some variance because the training performance is getting kind of low. It's around 6% by that point, but it's still fairly well separated from the test data. So we definitely have a bit of a couple of things going on. And what it leads us to believe is that, quite frankly, the features that we're using aren't really capturing the features that are necessary in order to differentiate these different classes on these documents. It's not surprising. Our bag of words model is kind of simplistic, right? We're just looking at the words that occur. And so if we dig a little deeper into the text reports, we can kind of get a sense of why this is happening. So intuitively, I would expect, and I think as a group when we discuss this, you would expect that the occurrence of anatomical keywords in the radiology report would likely indicate that there's something wrong with that particular structure. As it turns out, that's not really the case. Most of these text reports is a laundry list of anatomical structures that are all noted as basically not having anything wrong. And so that gives us a little bit of clue that that's not going to work just as it is. Likewise, if we look at an abnormal example, I mean, the first line certainly is sort of confirming our intuition, right? So the ossicles are mentioned, and there's, they're indicated as being dysmorphic. So that's kind of what we thought was going to happen. But if we look in the same document, there's also a number of other structures which are noted, but which are noted as unremarkable. And so we have to be a little bit smarter about how we might do this. So can we get better features with a little bit more sophisticated NLP? What I'd like to be able to do is count the occurrence of certain anatomical structures, provided they haven't been negated in some way. So in this first example, I'd want to count ossicles, but I would want to not count the other structures simply because they've been negated. And so we can do this with NLP. We're going to apply another open source tool. So PyConText was developed by Brian Chapman, who's currently at University of Utah. I believe he was at Berkeley, maybe somewhere in California when he actually developed this. But at any rate, it's a natural language processing tool built on regular expressions. If you're not familiar with regular expressions, essentially they're a sequence of characters which define a search pattern that can be applied over text. So for anyone in the audience who maybe is familiar with regex, I'll let you sort of stew over that first one for a bit. But they're not, for our use, they're not as scary as that one. We really just need to define target patterns. So these are regex patterns that will identify, in our case, the anatomical structures that we're interested in. These are fairly simple. I mean, it's just a couple of whole words with some relatively simple use of the special characters in regex. Additionally, we need to identify the context, in our case, negation patterns. Those are a bit more complicated, but still not too bad. This is one of the more complicated ones for identifying whether or not something is within upper or lower normal limits. And so for anybody who's wondering, the first one is a 10-digit phone number for the US with some optional punctuation. So what does PyConText do? It works on a sentence level. It scans each sentence, and as it moves through the sentence, it'll apply these regex patterns to see if it can find any of your target variables. If it finds the target variables, as it moves through, either forward or backward through the sentence, it'll also see if it finds a context pattern. So in this case, we have three, hopefully that's not me, we have three targets that we're interested in, and we also happen to find one negation context pattern, so R unremarkable. And so once it sees this context pattern, what it'll do is either search forward or backwards or both, depending on what you specified in the configuration, to see which targets that applies to. So it'll search, so in this case it's going to search backwards. It'll either find some targets and say, report that these targets have been negated, or it'll find another context pattern, in which case it'll sort of switch over to that one and then continue to look for either another target or another context pattern. And ultimately it reports out the occurrence of targets and whether or not they were modified. So we defined 16 target patterns with 61 negation patterns based on sort of manual review of our sample set. Now we applied, again, the chi-squared filter on this, and so we end up with actually just 12 of the target features being used. And so again, our purpose here is how can we convert our documents to features? And so what we're doing now is we take the output from PyConText and we convert the document to the number of occurrences of a particular target that wasn't negated. So in this first one, auditory canal was noted 3 times in the document without negation. You know, vestibular, for example, was either not in the document, or if it was always negated. Likewise, the last document, for example, either has no mention of any of these target variables, or any mention of the target variable was negated by something. And so that becomes our new feature set. And this performs quite a bit better. We end up with accuracy minus naive Bayes, which just is particularly poor again. Accuracy levels on the range of 95 to 97%. This is actually on par with human review. If you remember, one of the things I said that can go wrong in the sort of sample data that you have is that they're mislabeled. That absolutely happens. But more importantly, the thing that we were concerned about is our negative predictive value and our specificity. And these have gone up pretty much across the board. And in particular, on a couple of the models, we're at 92% was our high. And so we're doing pretty well there. And I'll get to why I've highlighted that one in a moment. And likewise, specificity has gone up. You know, we're in the 98% range here. And so we've significantly improved on the things, this sort of subpopulation of normal cases, while at the same time not, as you can see by positive predictive value and just accuracy, we haven't, you know, reduced performance on the positive cases. So that's a very good, I think, result. And if we look at a learning curve, we see that we've sort of eliminated, again, this is one sample learning curve out of 400, but we're getting down to sort of the kind of ideal performance that we would expect to have. The training data, the error, I think, is around 2%, and the test data error is maybe 3 or 4%, so we're kind of getting down into that, you know, where this performance is the same, and that's obviously as well as you're going to do. Your test data, you're never going to perform as well on your test data as you did on your training data, unless something has gone very drastically wrong. And so we feel pretty confident about that. And so then the next idea was, well, can we maybe sort of get specificity and negative predictive value to both be good? And maybe if we combine both the PyConText features and the bag of words features, maybe we'll have better results. Now, anybody who's really paying attention, we didn't combine them completely, or otherwise we'd have a 69 element vector. We applied a stricter threshold for the p-value on the chi-squared, so we end up with, I think it was 0.5% instead of 1%, and so we end up with 48 elements, again, trying to control overfitting. And what we find is kind of interesting. We end up flip-flopping the performance in specificity and negative predictive value. And so essentially what this is telling us is that we can control pretty well for false positives, or we can control pretty well for false negatives, but we really can't do both, at least not with the training set that we have. That is not uncommon. Most, well, maybe I shouldn't say most, but certainly many applied machine learning problems, that is an outcome that you observe, where you can control one or the other. And your decision about which one to control is really dependent on what you're trying to do. So if I was in a research setting, maybe I want higher recall, I don't really want to miss any of the, higher specificity, maybe I don't really want to miss any of the, I'm okay with missing some of the negative cases, but I really, I just want a larger set to make sure I'm getting or I'm sorry, more precise set, so I'm not dealing with things that aren't what I'm interested in. But in a clinical setting, maybe I want that higher recall because I don't want to let a sick patient kind of go by, or maybe depending on other factors that are important, you may be reversing that. So the point is there's decision criteria for your particular problem that are going to help you decide whether or not reducing false positives or false negatives is important and which way you're going to go on that model. And so as far as continuing work, a couple of things. So we're looking now at also using MetaMap. So MetaMap is another more full-blown natural language processing tool produced at the National Library of Medicine. And the advantage that it has over PyConText, if you recall, I said we had to specify these 16 anatomical keywords as our targets. And that's kind of a limitation because maybe there's another term that's being used that we failed to put into our target set that would clue us in on whether or not there's a abnormality in the ear. And so what MetaMap allows you to do, it has an ontology built into it. It's the UMLS, Unified Medical Language System. And so what we hypothesize that we can do there is say, just provide the keyword ear, and let the system decide that there's a number of substructures for the ear that are all part of the ontology, and that it will recognize these things, and so we don't have to do the work of specifying the targets. Not that specifying 16 targets was necessarily laborious, but if we miss something, then maybe we're not doing as well as we could given the training data that we have. So we're actually working on that now. The other thing that we'd like to do is be able to identify abnormal features. So if we've labeled a document as abnormal, can we say that it's the vestibular aqueduct that's enlarged, or can we say something else? To do that, we need more training data. The sort of limited set that we have is not enough for that, so we're actually working on that right now. And of course, I should point out some limitations. Obviously, I've spoken about the fact that we have a small training set. So there's some risk with that. They could be overfit because we have a small training set relative to the number of features that we have. The other issue is that this is a CHOP-specific training set. So there's some inherent assumptions there about whether or not this is representative, again, of the general population. There's certain language usage that may be sort of only done at CHOP that's not done at other institutions. So we're also working on, AugenDB is actually in the process of pulling in data from other institutions so we can test that moving forward. I put this slide in just if the slides are public and anybody's interested in being able to sort of like, okay, what are the tool sets used? Like I said, I kind of harped on that a lot of these things are open source and freely available because trying to prevent people who might want to do a similar kind of project from reinventing the wheel. And so this is the set of tools that we used. They're all Python-based because that was just sort of easiest for me, but there's a number of, there's R-based tools, there's Java-based tools. There's sort of equivalences of these out in public domain, but this is the stack that we used. So obviously I did not do this by myself, so some acknowledgements, and open the floor to questions.